All right, guys, here we go. So the date today is the 12th, and the topic for your notes today is reaction rates. So, guys, what I want to do to start the day is I want to tell you about the next class period. So once you're settled, let me explain to you what we're going to do next time, and that is going to help you to focus on what you need to get out of today. So, guys, this is the big idea. Guys, next time in class, we're going to come in, we're going to grade homework, and then you're going to go to lab. Now, do you remember what I told you about this lab as we were thinking through the fact that there's a lot of students gone today? Did I talk with your class about this a little bit? Oh, let me remind you. So, guys, when you go into lab on whatever day it is, when we go into lab next time, guys, this is what's going to happen. I'm going to hand you a lab sheet, and you guys are going to go into lab almost completely unprepared. Guys, as a matter of fact, on the lab sheet that you're going to get in the next class period, there is actually not a complete procedure. You guys are actually going to write your own procedures next time in class. So let me explain to you what you're going to try to accomplish in lab, and that'll help you figure out what you need to understand from today. So guys, this is what's going to happen. You guys are going to go into lab next time, and you're going to carry out an acid-base reaction. That's the tie back to what we did today and the homework that we just looked at. So guys, you are going to carry out an acid-base reaction. But what you're going to do is you're actually going to have a stopwatch. And when you pour the acid and the base together, you're going to start the stopwatch. And then guys, when the reaction is over, and we've got a really creative way to figure out when it's over, but guys, when the reaction is over, you're going to stop the stopwatch and you're going to write down the time. You will have just established a baseline speed, reaction rate. You will have just figured out a baseline speed for this reaction. Then guys, what you're going to do after that in lab with your lab partners is you are then going to write your own lab procedures, and you're going to figure out 3 different ways to make the lab go faster. You get the idea? So you are going to have to come up with 3 different changes. You can't do the same change 3 times. You're going to have to come up with 3 different changes, and then you're going to write procedures around that, and then you're going to test and see whether or not your ideas actually made the reaction go faster. You understand what you're doing next time? Okay, so guys, with that in mind, you have now got to be able to understand what determines how fast reactions go. So guys, this is the way today is going to unfold. We're going to start today by defining some terms. You're going to write them down. Then guys, we're going to have a brief but meaningful conversation about what determines how fast reactions go. Then, once you understand what determines how fast reactions go, we're then going to talk about what can we do to change that and make them go faster. And that's going to be our day. And then we're going to do homework, and then we're going to come back for the lab. You guys get the idea? Okay, so what are we doing first? Definitions. Here we go. So guys, grab something you can. Conceptual toolbox. So guys, definitions you need to know. Number 1, magnitude. We have heard this word a lot here in Utah County in the last couple months. Why? Because Lehi is getting shook up. Guys, I don't know if you have felt any of these earthquakes, but guys, if you live in North County, I've got friends up there that have actually been woken up as things are falling off of their shelves because of these little earthquakes that we've been experiencing. But guys, anytime an earthquake takes place, what do they tell you about the earthquake? Do you know? Yeah, the magnitude. They say this was a magnitude 2 earthquake, a magnitude 3 earthquake. The ones that happen down in the Caribbean that are really hurting people are like magnitude 7 earthquakes. Guys, it's called the Richter scale. By the way, the Richter scale is also logarithmic. But guys, when they tell you that it's a magnitude 2 or 3 earthquake, which is what these have been, what is that telling you? What does magnitude mean? Magnitude earthquake. What do you now know about the earthquake? Say it again. It's how strong it is, but what makes an earthquake strong? And guys, this is interesting. This is actually not how they judge tornadoes. Did you know that? Tornadoes are actually rated by the amount of damage they do. Guys, earthquakes are not. They're given magnitudes. And guys, do you know what the magnitude means? It is how strong, but it's a little deeper than that. It's actually how much energy it possesses. You can actually measure it in calories. You guys know that? The calorie is the unit of energy? Doesn't that make sense? Where do we get our food? Where do we get our energy from? Food, yeah. So you can actually measure the amount of energy in an earthquake in calories. It's a lot, but you can. So, guys, magnitude means energy. You settled on that term? Okay, here comes term number 2, frequency. Is it bugging you guys that my shoes squeak? It's bugging me. I've never taught barefoot. I'm gonna. There we go. I have socks on. All right. So, guys, frequency. Let me just define it for you. Well, let me try this. Guys, what if I told you that something happened frequently? It happened often, right? So, guys, frequency simply tells us how often an event takes place. If it has a high frequency, it happens a lot. If it has a low frequency, it happens less often. But, guys, frequency is how often an event takes place. Are we 2 for 2? Okay, so now, guys, thought number 3, reaction rate. Kind of makes sense, right? It's the topic for today. If we're going to talk about it, we should at least understand what it means. So, guys, some of you, probably many of you, have taken physics. And, guys, what is the definition of rate? Or even if you just know it casually and you haven't done physics, what does rate mean? What if you're driving down a highway and somebody asks you your rate of speed? What do they want to know? How fast you're going, in miles per hour. So, guys, rate is actually a measure of speed. It's a measure of how quickly something is happening. So, guys, in chemistry, reaction rate is the speed of the reaction. Now, guys, Jason or maybe Will or somebody over there, as we were talking about rate and I mentioned your car, they actually gave me units and they said miles per hour. Because, guys, your car travels miles over hours. But obviously, chemical reactions are not moving through space. So how are we going to measure the rate of a reaction? Well, guys, what do chemical reactions do? They make products. And how do we measure how much product a reaction makes? Moles. So, guys, our units for rate are moles per second. How many moles of product do they make in an amount of time? And in this case, that amount of time is the second. You guys doing okay? You're okay on magnitude, you're okay on frequency, and you're okay on reaction rate. You're okay? Okay, so guys, what I want to do now is I want to present to you the question that we are going to ask and answer to end the day. You're obviously not going to need to write any of this down, you'll see. But guys, this is the question that we're going to ask and answer at the end of the day. So guys, you're good on reaction rate? You're sure? Okay, here's the question. Which one of these two reactions has a higher reaction rate? First of all, let's talk about what they have in common. So guys, over here, we have a fireplace, could be a campfire. You feel kind of warm and cozy on a cold, wet day. And then guys, over here, frankly, I love this picture. What are we looking at? A metal ring. What do you suppose the purpose of that ring is? Maybe a door knocker. I could almost picture somebody tying a horse to it. I don't know why. But guys, where do you suppose this metal ring is? Where do you picture it? Not just a wall, right? It's not like at your house. I have no idea. I just know what I like. I don't know where this really is. It just makes me happy inside. Guys, where could you picture that ring being? I'm picturing a cabin or maybe a barn in the middle of nowhere. But guys, here's the question I have for you. Somebody put that ring there, right? Do you think it looked like this when they put it there? No, what's been happening to it? It's been rusting over years and years and years. So guys, here's the question I have for you. What do these two reactions have in common? Do you know? Say it again. Who said it? Yeah, guys, these are both reactions with oxygen. No oxygen, no fire, right, Boy Scouts? Right? But guys, no oxygen, no rust. So guys, these are both reactions with oxygen. So now let's come back to our original question. Guys, which one of these is happening faster? And the question is stupid, but let's say it. Which one's faster? Burning wood or rusting iron? Yeah, the burning wood, right? Guys, the question is why? And you don't know yet. But that's the question. We're going to bring this slide up at the end of the day, and you're going to be able to intelligently talk about why is burning faster than rusting, and you're also going to be able to talk about what could we do to make either one of these go faster, and that's the point of the lab on Tuesday. You get the idea? Okay, go ahead. You know what? It does not. Let's talk about that quickly. What about limiting reactants? So we can say this about limiting reactants. In this reaction, what's the limiting reactant in the burning of the wood? The wood, right? What's the limiting reactant over here? The metal. Yeah. So in both cases, the oxygen is not the limiting reactant. So yeah, I said that right. The oxygen is not the limiting reactant. What we can say is this. Because this reaction is faster, it will run out of the limiting reactant more quickly. But it doesn't have to do with limiting reactants. Is that okay? Okay, so guys, what does it have to do with? Grab something you can write with and let's get this stuff in our notes. So guys, fundamentally what we need to talk about is this. We're not ready yet to talk about how do we make reactions go faster. The first thing we need to talk about is what determines the speed of a reaction. And guys, that comes back to what's called, I know you normally don't write down the subheadings, please do. Actually, it's right there as well. Write it down and then we'll define it. Guys, this is what's called collision theory. You don't need to write down the question. It's simply to help us make the transition. So guys, the question we're asking right now is this. We're not talking about how to make them go faster or slower. Guys, the question that we're talking about right now is what has to happen for any reaction to happen, whether it's fast or slow. Do you know? Guys, the answer is actually this. It's called the collision theory of reaction rates. Scratch it down. This is what is called the collision theory of reaction rates. And guys, I like this teaching without shoes. This is amazingly, my wife's going to kill me because my socks are going to be really dirty, but I still like it. All right, so guys, what has to happen in order for a reaction to take place? So imagine that my right hand represents wood and my left hand represents oxygen. For these two things to react together, what do they have to do? They got to touch. Guys, literally, in order for a reaction to take place, the stuff that is reacting together has got to touch. I know this is annoying, but stick with me. So, guys, in order for the oxygen to react with the wood, the oxygen's got to hit the wood, right? So, guys, why is it that we can blow out a match? Because you can actually blow fast enough that you can blow the two apart. And when you do, the flame goes out. So guys, understand that in order for this, and what about for the iron to rust? Well, guys, those have got to hit as well, right? So guys, there has to be a collision for a reaction to happen. So guys, that's fundamentally it. You need to get this in your notes. For a reaction to occur, the reactants have got to collide. Now, guys, the question is why? It seems kind of obvious, right? For things to react together, they've got to touch. But it's actually not just enough for them to touch. They have got to touch hard. They have got to touch hard enough that the bonds inside the reactants break apart. An analogy that I like to talk about is that day when you get married. Guys, up until the day that you get married, you are in some sense bonded to your parents. But you want a recipe for disaster in your marriage? Marry somebody, but don't let go of your parents. It's a train wreck. Guys, when you get married, you have got to decide that the person that you're marrying, the person that you're bonding to, takes precedence over all others, and you got to let go of your folks. Guys, the exact same thing happens in chemistry. If you're going to bond to something else, you got to let go of the thing that you were bonded to first. And guys, that means that when these things hit, they've got to hit so hard that the reactants blow apart so that they can then form new bonds and make products. If you want to talk about the marriage thing more, we can do that later. So, guys, the idea is this. When they bond, when they react, they've got to hit so hard that the reactants blow apart, and then they can make products. Now, guys, the trick is this. Not all of these collisions are effective. This is kind of how this goes when you date in high school. You kind of get attracted to this person, but you don't hit that hard. You're still connected. Well, some of you, actually, that's not the case, but never mind. So, guys, the idea here, supposedly, is that if you're still bonded to your parents, and this guy comes, hey, you want to go to the dance? Sure, didn't go that great. There's not that tight a thing. You don't let go of your parents, and nothing forms. Okay, this is getting weird. But, guys, the idea here is that not all collisions work. Sometimes the reactants will bump into each other, but if they don't hit hard enough, they don't turn into products. They don't get married. They bump into each other, they fly apart, and they don't turn into products. So if they don't hit hard enough, no reaction occurs. So guys, based on that, what's the obvious question? How hard do they have to hit? Guys, in order for this reaction to happen, we have to be able to ask and answer the question, how hard do these things have to hit? And guys, there's an answer to that question, and this is the first big idea of the day. Ready? So the question then is, how hard do these things have to hit? You ready for the answer? I'm going to switch slides, but it follows in the notes. So do you understand the question that we're asking? In order for a reaction to take place, they've got to hit. That's collision theory. How hard do they have to hit? Well, they got to hit hard enough to break the bonds so they can form products. If they don't hit hard enough, no reaction takes place. So how hard is hard enough? And guys, the answer is this. It's called activation energy. So how hard these things have to hit? Activation energy. That's the answer. That's the question. So guys, how hard is that? Let me tell you, and then I'll show you. But guys, understand, the answer is not the same for every reaction, the answer is different. So let me define it for you. Guys, activation energy is defined as the minimum amount of energy needed for a reaction to occur. Now guys, this is weird, but just stick with me and this will make sense. You can think of activation energy as a hump. As a hump that exists between reactants and products. So guys, let me give you an example. You've all driven to Salt Lake, right? But it's not a straight shot. There's a hump between us and Salt Lake. What's it called? Point of the mountain, right? Guys, if you want to get to Salt Lake, you've got to have enough energy to get over Point of the Mountain. If you can't make it over Point of the Mountain, you're not going to make it to Salt Lake. So guys, there's a hump between us and Salt Lake. And if you don't get over that hump, it doesn't matter how hard or how bad you want to get to Salt Lake, you ain't going to get there if you can't get over Point of the Mountain. Well, guys, the same thing is true in reactions. There's a hump that separates reactants and products. And if they don't hit with enough energy to get over the hump, they don't make it to Salt Lake. They don't complete the trip. So, guys, this then determines how fast a reaction goes. The more collisions that get over the hump, the faster the reaction goes. So guys, imagine that we want to move a bunch of people up to Salt Lake and they're all driving their own cars. Well, the more cars that can get over Point of the Mountain, the faster we'll fill up Salt Lake. Guys, similarly, with reactions, the more collisions that can get over the hump, the faster the reactants become products. You guys okay? You're good? Okay, so guys, the Point of the Mountain analogy is good, but let me give you another analogy. And guys, you understand that analogies are never perfect. There's always going to be things that we have to sort of ignore for an analogy to work. So let me give you another analogy. Guys, have you all made the mistake of playing this hole on a putt-putt course? If you take a date, again, we're back to dating and marriage. If you ever take a date putt-putt golfing, guys, do everything that you can to avoid playing this hole. This is a no-win situation. It's like taking a first date out for chicken. You can't win. Because guys, if you take a first date out for chicken, there's no way you can do this right. Because either you're going to grab the bone and look like a Neanderthal, or you're going to eat it with a fork and knife and look like a sissy, right? You can't win. Do not take a date for chicken. Guys, the same way, do not ever play this hole on a putt-putt course, because you can't win. Because guys, what happens if you try to finesse this? What happens if you just try to kiss the ball and get it to go over the hill? What's it going to do? Stops just short and rolls back to your feet and you look like an idiot, right? So I've never done this with a date, but I did do this with my son, Cody, when he was about 8. And that's what happened to Cody. The ball rolled up and then it rolled back down. So in the mind of an 8-year-old boy, if that doesn't go well, what do? You wind up on that thing. And guys, this was up on 800 North. And Cody, the second time, wound up on that ball and shot it all the way across 800 North to the helipad over at the drug rehab center. He was like, crack, and that ball went flying. So, guys, you understand sort of the weirdness of this hole. There's a hump. And if you want to get over the hump, you have to hit it with enough energy to get over the hump. If you don't, the ball rolls back as if nothing happened. Well, guys, this, though, is where the analogy falls apart. So for this analogy to work, we need to make 2 assumptions. Assumption number 1 is this. Any ball that gets over the hump goes in the hole. Okay? Assumption number 1 is this. And so you don't have the Cody option of knocking the ball over across 800 North. So guys, any collision, any ball that gets over the hump goes in the hole. Guys, the other thing that's not quite right about this analogy is this. When the putter hits the ball, they actually stick together and the putter goes in the hole too. Told you, it's not perfect. But guys, here then is the question. If our goal, listen carefully because this is about to become important. Guys, if our goal is to get balls in the hole, and realize it's really balls and putters, but if our goal is to get balls in the hole, what can we do? What can we do to get as many balls in that hole as fast as we possibly can? First thing we need to do is we need a bunch of balls, right? Imagine if we went ting, and then we waited 10 seconds and went ting, and then we waited 10 seconds and we went ting, and then we waited. That's not going to work. We got to go boom, 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 boom. We want to hit these balls with a, hold on. We want to hit these balls with a very high, look at the top of your notes, with what? Very high frequency, right? Guys, in order for this to work, you see how this is coming together? In order for us to fill up that ball quick, we want to hit the balls with a really high frequency. But guys, what if we do this? What if we hit the balls with a really high frequency, but we sissify this, and we're like, ping, 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 ping. Guys, what do we want to do when we hit these balls? It's got to be fun. Crack, 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 crack. Guys, we want to be knocking the bajinkers out of this ball. Because remember, every ball that gets over the hump goes in the hole. So we want to not only hit these balls very frequently, we also want to hit them with high magnitude. You get the idea? Okay, so guys, here's the deal. Not only does this work in doesn't work in putt-putt golf, but not only does this pretend to work in putt-putt golf, it also works in chemistry. Guys, check out the picture. Scratch it in your notes. Draw this with me. So guys, draw an XY line, or just a set of axes. Let me switch colors. So guys, draw a set of axes, a Y and an X-axis. And then guys, on the X-axis, please write time, and on the Y-axis, energy. So guys, this is the way that this goes. When a reaction starts, we have reactants. Please write that down about where it is in the graph. When a reaction starts, we have reactants. When a reaction ends, what do we end up with? Products. Please write that over here a little bit lower than the reactants. But guys, now connect the two. But guys, watch. Don't do this. Just watch. Connect the two. But you'll notice the connection's not that. Reactants do not just turn into products and lose energy. Guys, what has to happen is they've got to collide with enough energy to get over this energy barrier. And if they get over, they then spontaneously turn into products. And what do we call that hump between reactants and products? Activation energy. Do you now feel like you understand activation energy? Is that okay? Because guys, if you understand this idea of activation energy and that the speed of the reaction is dependent upon the number of collisions that get over that hump, guys, we only have one more thing to talk about. How can we get more collisions over the hump? We figured it out talking about putt-putt. Hit them really fast and hit them really hard. But guys, the question is, how do we make similar changes if we're not talking about putt-putt balls, but we're actually talking about reactants and products chemically? So do you understand where we're headed to finish out the day? And guys, I pray that you've made the connection that the things that we are about to talk about are the things that you're going to be thinking about in lab next time. Did that make sense? Madeline, you with me? You guys with me? Guys, did that make sense? Guys, the things that we are about to talk about are the very things that you're going to be thinking about and writing procedures towards when we do the lab next time. Do you understand where we're headed? Okay, so here we go. So guys, we're now ready to talk about how we relate this to next time's lab. And this is just a review of what we talked about with the putt-putt stuff. Guys, can we all agree with this? For a reaction to go faster, more of the collisions have got to get over the hump, right? So how do we do that? Well, we've already established that we can do this by increasing the magnitude or increasing the frequency of the collisions. We okay with that idea? They got to hit harder or they got to hit more often. So now, guys, the way that we're going to wrap up the day is this. How do we accomplish that? How do we get them to hit harder? How do we get them to hit more frequently? And I'm going to give you 4 ideas. And then we're going to come back to our picture and talk about why wood burns faster than iron rusts. You guys ready to go? So guys, the question is this: how do we do this? How do we make them hit harder? How do we make them hit more often? Well, guys, the first way is this. Scratch this down with me. Temperature. How do you make a reaction go faster? Heat it up. So guys, I'm just going to give this to you. Let me even ask you. Guys, will hot reactions go faster or slower? You understand that's why you own a refrigerator, right? Guys, what does a refrigerator fundamentally do? It is a reaction rate suppression chamber. Guys, when you go to the grocery store and you buy a gallon of milk and you bring that gallon of milk home, the clock is started. And your goal is to try to drink that milk before it rots. So there's two ways you can do that. You can either drink it really fast, or what else can you do? Get it to rot slower. And that's why you put it in a fridge. The milk gets cold and the reactions that make it rot slow down. And as a result, you have a better chance of drinking it before you can't. Because that's all refrigerators. Freezers even more so. You freeze them and the reactions slow down so much that you can keep stuff indefinitely. But guys, temperature affects the speed of a reaction. And it goes like this. If cold slows it down, hot speeds it up. So as the temperature goes up, the rate goes up. You guys ever think of a refrigerator that way? I didn't think so. Every day. Liar. You just know it's a place to go if you're starving. But guys, here's the question. Why? Why do hotter reactions go faster? Now guys, please write this down with me, but this is not the answer. There's only two choices. The answer to this question can only have two choices, two answers. It's either frequency or it's magnitude. So let's write them both down. But it may not be both. So guys, once you've written down the words frequency and magnitude, stop writing and let's talk about this. So the question that we're asking is this: why do hot reactions go faster? And guys, the answer has got to be either the frequency of the collisions or the magnitude of the collisions. To figure out which it is, you need to know the difference between hot and cold. So, the one on the left is hot and the one on the right is cold. So what is the difference between hot and cold? Divert your eyes. Here comes Naked Boy. Oh, actually, no. Here comes Turtle Guy first. So guys, what is true? Now you're scared of Naked Boy. Guys, what is true of things that are cold? They're moving slow. Okay, here he comes. But guys, what is true of things that are hot? I don't know why, but he makes me happy. They're moving fast. So guys, fundamentally the idea is this. Hot things are moving fast, cold things are moving slow. So you ready? Let's talk about hot. So guys, if things are hot, they're moving faster. And if they're moving faster, do they collide more frequently? Circle it. Yeah, it is a matter of frequency. But if they're moving faster, do they collide harder? Yes. Guys, it's both. And I will tell you right now, this is the only change that double dips. All the other changes that we're going to talk about affect one or the other, but not both. Guys, temperature double dips. It affects the frequency and the magnitude of the collisions. You good on that? Next change. Guys, the next thing that you can change is concentration. Reviewing for the final, what are our units for concentration? Molarity. So guys, molarity, concentration, changes the rate of a reaction. Let me just give it to you. The higher the molarity, the faster the reaction. Concentration goes up, rate goes up. But again, guys, the question is why? And again, there's only two possible answers, right? It's either magnitude or frequency. And we're going to figure out which one. You know it's not both, because I already told you temperature is the only one that does both. Now we've got to figure out which one it is. So guys, let me share with you another analogy. So let me show you the difference between high and low concentration. And then the question that we're going to figure out is what happens to the collisions in both of these settings. So guys, high concentration. This is Cornhusker Stadium on any Saturday in October. Guys, you understand that the only way to get tickets to a Nebraska Cornhusker football game is if somebody dies. Seriously, it's true. People leave their season tickets to their children in their wills. You can't get tickets to a Cornhusker game. Guys, this is very, very high concentration. Now, this is low concentration. This is actually an aerial shot up in Salt Lake. What's the name of the plaza? This isn't in a football game. It's a Gallivan Center. Guys, this is actually an aerial shot. There used to be anyway, it doesn't matter. So guys, we've got people wandering around in a plaza at lunch, and we've got people moving around in a football stadium. Guys, what will be the difference in terms of their collisions? These people could run into each other. These people could run into each other. So let's talk about frequency. Is there a difference in the frequency of the collisions? Oh yeah, who's going to collide with people more often? Cornhusker fans or people going to lunch? Cornhusker fans. So guys, there is a difference in frequency. What about magnitude? Do they hit harder? No. They just hit more frequently. So guys, this is a matter of this is a matter of frequency, and the higher concentration systems will collide more frequently. The rate of a reaction is surface area. So let me just give it to you. Guys, the relationship is this. The higher the surface area, the faster the rate. But again, the question is why? Is it frequency or is it magnitude of the collisions? Again, to answer this, I'm going to give you a real-world example. Now, guys, understand that this is not an example that I'm going to be able to use much longer in Utah because the church has abandoned Boy Scouting. I don't know what they're going to use to replace it. But guys, currently, most of the guys in this room have gone through the Boy Scout program, or at least what Utah has turned Boy Scouting into. Guys, my little commentary, well, never mind, I won't comment. But many of you think that camping involves driving 20 minutes out of town, stacking up a bunch of pallets, dousing them in gasoline, lighting them on fire, and being back home by 8 o'clock the next morning. That's called Boy Scout camping. Guys, we're going to talk about what this is really supposed to look like. And it goes like this. Guys, imagine if you were challenged with starting a fire, but you don't get to use gasoline. Could you imagine trying to start a fire by sticking a match to one of these? No, some of you are going, yeah, just add gasoline. No, guys, you would never get one of these logs to burn by holding a match to it. So what do you have to do to get, you need tinder, you need kindling. And so guys, for those of you that are trusted with sharp objects, they give you a little hatchet or an axe, and you take this wood and you split it into kindling, and now it'll light. Because the question is why? Why does kindling light but wood won't? And here's the answer. Imagine that you have a log that's a cylinder. Where's the surface area? On the outside. So guys, if you take that log and split it with an axe, it opens up. And guess what you've just done? created more surface area because the part that was on the inside is now on the surface. And if you do that again and again and again and again and again, you create enough surface area that now a match can light that thing that was previously not flammable. The question is why? Why does extra surface area make things more flammable? Is it a question of frequency or magnitude? So guys, what has to happen in order for the wood to burn? What does it have to collide with? Oxygen. And if you've got a log, the oxygen can only hit it on the outside. But if you split it open, you're creating all these other surfaces where they can collide. Therefore, the oxygen in the wood will collide more frequently, and as a result, you can get it to burn. It doesn't collide harder. You're not speeding anything up. You're just allowing them to collide more frequently, and therefore things combust. You guys okay? So what are the three things that we know that speed up reaction rates? Guys, one of them is temperature. The second one is concentration. The third one is surface area. You ready for the last one? Here we go. Guys, the last one are what we call catalysts. Now guys, let me tell you right now, in the lab that you're going to do next time, there is not a catalyst for the reaction you're going to do. So this is not one of your answers in lab, but we're going to talk about it. So guys, what is a catalyst? A catalyst is a substance that speeds up a reaction without it being consumed. It's like a cheerleader. It encourages the reaction, but it's not part of the game. Guys, catalysts are the same. They encourage reactions, they speed reactions, and some of you are going, how does that work? Come back for AP, it's actually really cool. So guys, they are things that speed reactions, but they're not involved. As a result, this is not a function of frequency and it's not a function of magnitude. And now you're going, wait a minute. I thought you said that we have to change the frequency or change the magnitude to get a reaction to go. And now you're telling me catalysts don't change the frequency and they don't change the magnitude, but they make the reaction go faster. Yeah, that's exactly what I'm telling you. So guys, the question is this: how can a catalyst make the reaction faster if it doesn't make them hit harder and it doesn't make them hit more frequently? That's it. It lowers the hump. Guys, catalysts actually create what are called new reaction pathways. And these reaction pathways have a lower hump. It's like taking a bulldozer and knocking down Point of the Mountain. Now you don't have to have as much energy to get to Salt Lake because the hump is lower. So guys, if you would go back then, please, to this drawing, draw in a new pathway that has been catalyzed. Just scratch it in your notes. What do you think it's going to look like? Start at reactants, draw a line to the products, but now draw a line that you think represents what it'll look like with a catalyst. And guys, it actually looks like this. A catalyzed reaction simply has a lower hump. How we doing, team? You guys okay? So guys, let's do this. Once you've drawn in your picture, you're good. Let's go back to our original question and let's figure this out. You ready? This is actually really interesting. Try this with me. Guys, there's so many answers. You ready to go? Here we go. Guys, why? Why do the logs burn faster than the iron rust, given everything that you just learned? Good. This is hotter. Guys, this thing releases energy that speeds up the air and speeds up the wood molecules, and they collide harder and faster. Guys, why else does wood burn more quickly? Good, it has more surface area. Did you guys know you can change that? You can actually take iron and create so much surface area that the reaction happens so quickly it actually produces a lot of heat. They sell these. They're the hand warmers that you shove inside your gloves when you're skiing. Guys, those stupid little packets that you can buy for like $1, what do you have to do to get them to work? Well, you have to rip the package open. And when you do, you are simply exposing what's inside there to oxygen, to the air. You want to know what's in there? Ground up nails. Seriously, guys, that's all, well, and another little thing, there's a catalyst. But the only thing that's in there is ground up iron. And that all that extra surface area makes the iron rust so quickly that it generates heat and it keeps your hands warm. But it is a question of surface area. Guys, what else? Concentration? Nah, not really. But guys, there's actually one other, and you won't find this surprising. Guys, this is actually what the reaction pathway looks like for burning wood. It has got a relatively low activation energy. What do you suppose the activation energy hump looks like for iron? It's high. Guys, why would the activation energy be higher in iron? Because iron is hard. It's all bound together and it's got to break apart in order to react. And these things are so tightly bound together that this stuff doesn't want to blow apart, so it takes a lot of energy to get it to blow apart and turn into rust. And guys, for all of these reasons, wood reacts faster than iron does with oxygen. Do you get the idea? Because you've learned a ton today. Look at your homework packets really quickly. It's taken me 26 years to figure out to teach without shoes. This is life-changing stuff. So guys, we are now on homework assignment number 2. You won't find this as difficult as homework assignment 1. This is synthetic in that it's asking you to take some of the things that you've learned and apply it in new settings, but I think you're going to find this material much more accessible. So guys, do the homework assignment. We will grade both homework assignments on, well, when I see you next. And then we'll get you into lab and see if you can speed up some reactions. Yeah. That's a really good, so Jason's question is, what is an example of a catalyst? And actually, it's interesting. There are these group of metals called the universal catalysts. They're actually platinum, palladium, and what's the other one? Is it platinum, palladium, and I want to say ruthenium, but I'm not exactly sure. It's so these are actually what are called universal catalysts. And the thing that makes them catalysts is that they have these little weird points of polarity on the surface of the metal that grabs a hold of reactants and holds them in place so they can react faster. So, like if you've ever heard of the catalytic converter in your car, I don't know if you even know what that is. So out of the back end of your engine, you've got the exhaust pipe, right? And eventually it hits the muffler. But right before the muffler, it hits this thing called the catalytic converter. And it's actually a canister full of these little ceramic pellets that are coated in platinum. And as your exhaust goes through that matrix of little platinum balls, it actually causes the exhaust gases to react more completely, and that cuts down on the amount of pollution that your car spits out the back. It turns out, though, that platinum is really expensive. I mean, we make jewelry out of it, right? And do you guys remember this? It was like 6 or 7 years ago after Christmas break, Jordan School District, the bus drivers came back to work after Christmas break, and somebody had broken into their bus lot and cut all the catalytic converters out of all of their buses. Yeah, they stole the catalytic converters out of all of the buses, and they took all the platinum and melted it down and sold it. So, and then none of these kids could go to school. It was really slimy. So anyway, guys, questions? You guys are good? Okay. Have a good weekend. We will see you after the weekend.